For lecture 9, we're going to return to reactions of the carbonyl. We're going to be looking at ketones and aldehydes. So both functional groups, ketones and aldehydes, are based on the carbonyl. Carbonyl is the C double bond O functional group. A ketone, remember, is a carbonyl that contains two R groups. Specifically, those would be carbon R groups. The aldehyde specifically is a carbonyl containing at least one hydrogen. Remember that two hydrogens is called formaldehyde. If it's only got one hydrogen, it could be any variety of aldehydes. If there are no hydrogens on the carbonyl, it's a ketone. Other common classes of carbonyl compounds that are based, of course, on the carbonyl, we have ketones and aldehydes. The acid chloride, which is one of our reagents that we used in the Friedel-Crafts acylation, that's an acid chloride. And also carboxylic acids we have. We're going to have a few chapters later on carboxylic acids. We also have esters, in which the carbonyl has an OR group, and amides, in which the carbonyl has an amino group on it. The carbonyl is a pretty straightforward chemical structure. Both the carbon and the oxygen in the carbonyl are, of course, sp2 hybridized, meaning that there's a sigma bond and a pi bond constituting the double bond. That means that the two groups that are immediately bonded to the carbon are planar. So in a ketone, the two R groups are planar, and in an aldehyde, the R and the H group would be planar. Also, just note that because the oxygen is also sp2 hybridized, it too is planar, which means that its two lone pairs are going to be in the same plane as the two groups on the carbon. So basically all four of the things, all four of the electron domains that are attached to the carbonyl will be planar, the two groups on the carbon and the two groups on the oxygen. We talked about the carbonyl being a good electrophile. We used it as a reaction partner with Grignard reagents, for example. Remember that the carbonyl is electrophilic due to the CO dipole, the carbon-oxygen dipole, and also the high-energy reactive carbon-oxygen pi bond. Comparing the carbon-oxygen double bond to a carbon-carbon double bond, you see that the carbon-oxygen double bond is shorter and higher energy. It's more reactive. The carbonyl has two resonance structures where we could take a pi bonding pair and move it from the bonding domain onto the oxygen. That would get us an O- and a C+. That's, of course, the minor resonance structure, but this explains the origin of the dipole. We have partial positive charge on the carbon and partial negative charge on the oxygen. The dipole in acetaldehyde, a methyl aldehyde, if you will, is 2.7 dBi, and on acetone is 2.9 dBi. So these are relatively polar functional groups. Let's talk very briefly about nomenclature of these groups. Generally speaking, the ketone is named as an alkanone, and the aldehyde is named as an alkanal. In naming ketones and aldehydes, the carbonyl typically gets the highest priority of any other substituents. You can think of it as a carbon bonded to two oxygen atoms, or a carbon with two bonds to O. So because of that, it's a high priority group. Now, in a ketone, often it is the case that the carbonyl can exist in multiple positions. For example, in a pentanone, a 5-carbon ketone, you can have the double bond on the second or the third carbon. So in the event that you have a ketone where the carbonyl could exist in different positions, we need to indicate the position of the carbonyl using a number. So if our template is going to be alkanone, if it's a 4-carbon ketone, it's going to be butanone. But for 4 carbons and anone for ketone. Here, the only position, notice, that our ketone can be in is in the 2 position. If our carbonyl is on the 1 carbon, it's not going to be a ketone anymore. It's going to be an aldehyde. So there's only one really logical position that you can have a carbonyl for a ketone on butanone. So you don't really need to say 2-butanone or splitting the root butan-2-one. But that's how you would do it. If we would have a pentanone, for example, here's a 5-carbon chain. Notice that ignoring these methyl groups as substituents, you could have a carbonyl on the second carbon, it would be a ketone, or on the third carbon, it would be a ketone. So in this case, we have to designate that this is a 3-pentanone or a pentan-3-one. So this would be 2,4-dimethyl pentan-3-one. Now here's a little bit of an interesting structure because you wouldn't normally have a 1-propanone. A carbonyl on the 1 carbon of a 3-carbon chain is technically an aldehyde. If it's at the end of the chain on the 1 carbon, it would be an aldehyde. But in this case, they're using the phenyl group as a substituent. So we're going to call this 1-phenyl, 1-propanone. So technically, this is not the end of the carbon chain, so that's why it's a ketone. But as far as nomenclature goes, we could name this as a 3-carbon chain with a ketone on the first carbon and a phenyl group on the first carbon. Here's 3-methyl cyclopentanone. Notice that the indication of the 1 ketone is ignored because in a ring, the highest priority group will always get 1 by default. So 3-methyl cyclopentanone indicates that the methyl is on the 3, and it is implied that the ketone is then on the 1. Notice that in the case that we have a double bond O and a double bond C in the same structure, the double bond O takes priority. Again, think of this carbon as having 2 bonds to O as opposed to this carbon having 2 bonds to C. Having higher molecular weight groups gives you higher priority. So this would be 2-cyclohexenone. Now again, what does the 2 refer to? It can be a little bit ambiguous. Is the 2 referring to the one, or is it referring to the ene? Well, if you know your IUPAC, you would assume that the ketone is higher priority, and therefore the 2 implies the location of the double bond, the same way that the 3 implied the position of the methyl group over here. So that would be 2-cyclohexanone. Of course, we can get a little bit more precise by splitting the root. Cyclohex 2-ene-1-one. You could even just say cyclohex 2-enone, but at least if you're splitting the root, this gives us the opportunity to insert the number that indicates the location of each functional group, a 2-n-1-one. Here's 4-hydroxy 4-methyl-2-pentanone. They've named this as a pentanone, a 5-carbon ketone, with the ketone on the 2, so a 2-pentanone. That gives us a 4-hydroxy group and a 4-methyl group. Remember, we've learned how to name alcohols. If you want to name this as an alcohol root, it would be a 2-pentanol. The question then becomes, if you name this as a 2-pentanol, meaning a pentane with a 2-alcohol, it then is also a 2-methyl, but how would you name the ketone as a substituent? I'll show you a little bit later that the ketone as a substituent is named as an oxo group. But if you want to name this as a ketone root, it would be a 2-pentanone with a 4-hydroxy and a 4-methyl. So 4-hydroxy, 4-methyl pentan-2-one. Aldehydes being alkanal, a little bit simpler because by definition, the aldehyde is always going to be on the 1 carbon of the chain. So saying the location of the aldehyde is not really necessary. So we have ethanal here, which would be a 2-carbon aldehyde. Here's a heptanal, a 7-carbon aldehyde. Of course, we're going to number from the end that contains the aldehyde. That gives us a 3-methyl and a 4-bromo. You line those up alphabetically, so 4-bromo, 3-methyl heptanal. Here's 3-hydroxybutanal. Again, this is named as a butanal instead of a butanol because the aldehyde has higher priority than the alcohol because that carbon is connected to more heavy groups. Here's pentenal. Again, we number from the 1 carbon with the aldehyde, which by definition puts the ene on the 2 carbon. So 2-pentenal or pent pent-2-enal. I guess you could split it farther and say pent-2-en-1-al, but then again, the aldehyde can only be on the first carbon. Sometimes the aldehyde will be a group coming off of a ring or off of some other main chain. In this context, sometimes it's named as a carbaldehyde, a single carbon aldehyde as a kind of substituent. So this is cyclohexane carbaldehyde or 2-hydroxy cyclopentane 1-carbaldehyde. It's kind of named as a substituent, but it's also kind of tacked on the end as a root would be. We're not going to see many groups like this, but in general, an HC double bond O is a substituent. You could call it a carbaldehyde group. Now we've seen lots of reactions that involve ketones and aldehydes already. One of our first oxidation reactions was converting secondary alcohols into ketones. You could do that with any number of oxidizing agents like chromic acid, sodium chromate, PCC, Sorn oxidation. Lots of reactions to convert secondary alcohols into ketones. We could also convert aldehydes into secondary alcohols by doing a Grignard reaction. Take the aldehyde, use it as an electrophile alongside a Grignard, add that R group to our carbonyl carbon, displace the electrons onto the oxygen, protonate it, and you get an alcohol. You can then oxidize that alcohol to the ketone. You could also make the aldehydes from an oxidizing agent, for example, converting a primary alcohol into an aldehyde. Remember, that was the specific use case for a Swern or PCC oxidation. If you continue on with a stronger oxidizing agent, the aldehyde will then, of course, be converted into the carboxylic acid. We've also seen ozonolysis, oxidative cleavage of an alkene. In the case that you have a carbon that has a hydrogen on it in our alkene, that carbon will be split off into an aldehyde. Ozonolysis specifically was the oxidizing agent that would cleave the double bond but not oxidize the hydrogen to an oxygen. That's another way to get aldehydes, is by cleaving a double bond by ozonolysis. Another method of making ketones, we could do it from, say, a Friedel-Crafts acylation, starting from an acyl chloride, like an acid chloride here. Add that onto an aromatic ring by means of a Friedel-Crafts acylation along with our Lewis acid. That would go onto our ring in the appropriate position relative to any other group on the ring. For example, if R is an alkyl group, that would be an ortho-para director, so we would put our acyl group on para to our group. Of course, we could also have ortho, that would be the minor product. If this is a meta-director, if G is a meta-director, our ring will be deactivated and we might not get very good yields. So the meta product in a meta-directing group might not be very high yield. So if these are activated rings, this is a great way to make a ketone. We've also made ketones by Markovnikov addition to alkynes. Remember, using our mercury and H2SO4 and water addition, that gives us Markovnikov addition of water across the triple bond, where you put the OH on the more substituted side, the H on the carbon with the most H's. That's Markovnikov's rule. That gives us an enol, which is not isolated, it's not stable. That tautomerizes into the ketone. If we go anti-Markovnikov, using the cyamyl borohydride reagent, that goes the opposite direction, putting the OH on the less substituted carbon and the H on the more substituted carbon. That's still an enol. Then we tautomerize our alcohol into the carbonyl. We end up with an aldehyde instead of a ketone. A new reaction that's kind of cool is a synthesis of aldehydes or ketones using a functional group called a 1,3-dithiane. This is a 1,3-dithiane. Remember, thiones are kind of the sulfur analog of ethers. And in a ring, we call this a 1,3-dithiane. These hydrogens are very mildly acidic. They have a pKa of 32, which on the pKa scale is pretty high. Of course, they're connected to carbons, and most of the time hydrogens and carbons are not very acidic. But if we have a very strong base, like a butyllithium reagent, N-butyllithium for example, a very strong base will happily remove one of these hydrogens, giving us this dithiane anion. Now, the reason why these hydrogens are acidic at all is because when they are removed as an H plus and you give a negative charge with a lone pair to that carbon, you have two sulfurs on that carbon that are able to kind of inductively pull that electron density away owing to their electronegativity. Just for comparison's sake, remember that the pKa of an alkane like butane is 54. So comparing the acidity of butane to the acidity of dithiane, our dithiane is much more acidic. So if we have the conjugate base of butane and butyllithium, the reaction will proceed forward to move the negative charge from the worse carbon to the better carbon. So once we make our dithiane anion, we can use it as a nucleophile to add to an alkylating agent, some Rx group. Usually that's going to be a primary alkyl halide. I'll mention that in a moment. This will be a primary alkyl halide. That gives us the ability to add our R group specifically onto the carbon that has the two sulfur groups. Now, in the presence of mercury chloride and acidified water, H3O plus, for example, the dithiane is oxidized to the aldehyde. So notice that whatever R group we chose to put on our dithiane by means of our alkylating agent is the R group that ends up on the aldehyde. So if we want a methylaldehyde, we use a methylating agent with dithiane. If we want an ethylaldehyde, we use an ethylating agent and dithiane. Whatever R group we want, we can put that onto the dithiane and then oxidize it to the aldehyde. Now, couple gotchas here. There can't be any acidic hydrogens on the Rx alkylating agent. We're not allowed to have alcohols or any other acidic hydrogens on here because the dithiane is such a strong base. If there are any acidic hydrogens, it will simply grab those acidic hydrogens rather than attacking the R group the way that we want it to. Secondly, we mentioned that this leaving group on the Rx must be primary because this is first of all an SN2 reaction and our dithiane anion is quite bulky. Remember that in SN2, generally speaking, we need a very good nucleophile, a strong nucleophile, first of all, with a high negative charge on it. But it's also going to be small because in the SN2 mechanism, the nucleophile has to access the antibonding orbital of that Rx bond. So the fact that our dithiane is so bulky means that we are not going to be able to do SN2 on, say, a secondary halide. We can only get away with primary or perhaps methyl alkyl halides here. But keep this in mind as a creative way, a very flexible way of making any particular type of aldehyde you might want. You can also make ketones from carboxylic acids. This is a little bit of a messy reaction. It says an excess of an organometallic reagent can add to a carboxylic acid to form a hydrate, which loses water to form a carbonyl or ketone. So for example, here's a carboxylic acid, and we're going to use an excess of phenolithium. So 2 equivalents of phenolithium, meaning for every mole of cyclohexane carboxylic acid we have, we're going to use 2 moles of phenolithium. Notice what happens is one of the moles of the phenolithium is used up. It goes away. It doesn't end up on our product. We've got 2 aromatic rings here, and throughout our reaction, we only have 1 aromatic ring. That's because our carboxylic acid is a strong acid, which means that if we have a very basic reagent like phenolithium, the phenolithium is going to react with the carboxylic acid before doing any other type of nucleophilic addition. So 1 full equivalent of our phenolithium is used up by deprotonating the oxygen. The second lithium reagent will add to the carbonyl, kick up the electrons onto the oxygen, and that gives us our one addition. Notice that we have a dianion because one oxygen got deprotonated by the phenolithium, so we have the O lithium there, and the other oxygen turned into an O minus when the lithium reagent attacked the carbonyl. So we have our two lithium ions are pairing with our dianion there. If we protonate that, we reacidify the solution, we will convert our dianion into a hydrate, which is a geminal diol. And typically hydrates are not stable. They tend to lose water and regenerate the C double bond O. So notice that we've taken the carboxylic acid and using two equivalents of R, Li, we end up with adding the R group in place of where our carboxylic acid group was. So why two equivalents? We talked about that because we have to use up one of our equivalents to deprotonate the carboxylic acid hydrogen. This strategy may not be feasible if your, say, lithium reagent is expensive. If it's very expensive or, say, laborious to make or buy your lithium reagent, you don't want to do a reaction wherein 50% of that lithium reagent goes to waste. So again, a little bit of a messy reaction. If your lithium reagent is cheap, then who cares? But if it's expensive, it's probably not really a feasible way to do it. We'll talk about the mechanism of dehydration in class, the mechanism of losing water from our geminal diol to our ketone. We'll do that in class. If you want to take a shot at it on your own, go for it. It's not a difficult mechanism. You can probably figure it out. You notice that it happens in the presence of acid, H3O plus acidified water. See if you can figure that out. We can also make ketones from nitriles. Nitriles are RC double bond N. That's sometimes called a cyano group, but the R with the cyano group is called a nitrile. And we can make ketones from nitriles. Generally speaking, what you'll do is you'll start with a nitrile and you'll add a Grignard or lithium reagent to it. The nitrile, like a carbonyl, is susceptible to nucleophilic attack because the carbon has partially positive charge and the nitrogen is willing to accept the pi electrons as the leaving group. So our Grignard will add our R group onto our nitrile carbon, kick the electrons up onto the nitrogen. That gives us an N minus that pairs up with the Mg plus. That's the salt of our what's called an imine. If we protonate that, neutralize the reaction, reacidify the solution, our MgX will fall off and we'll end up with our neutral group. This is an imine. The C double bond NH is an imine. If we add acidified water, again, H3O plus, to our imine, we will get a ketone. So this is the hydrolysis mechanism of a nitrile into a ketone. And again, if you want to try to figure out this mechanism, converting the imine into the ketone using H3O plus and water, we'll figure that out. Go for it. Take a shot at it. We will do it in class as well, and I'll post a note on it on Canvas. We can also make aldehydes or ketones by means of an acid chloride. Again, we use the acid chloride as a reaction partner in the Friedel-Crafts acylation, but we can also add nucleophiles to it. Now, when we did Grignard reactions and lithium reagent reactions, remember that the acid chloride was one of these special carbonyls that allowed the Grignard or lithium reagent to add two equivalents. Remember, the first addition added to the carbonyl, the electrons would go up onto the O, they would fall back down off of the oxygen and displace the chloride. That would get us a ketone with one addition, and then our second addition would add back into the ketone, and eventually we'd have our alcohol with two R groups added to it. Remember, that was what the acid chloride did in the presence of a lithium or Grignard reagent. Here I'm showing you two new special reagents that will only add once to those special carbonyls. Acid chlorides and esters were those special carbonyls. The two special reagents that I'm going to show you here will only add once. The first one is lithium triterbutoxy aluminum hydride. Now, this looks a little bit like LiAlH4, lithium aluminum hydride, except notice that 3 of the 4 hydrides have been replaced with T-butoxy groups. These are inert, if nothing else basic, T-butoxy groups. What this does is it causes the hydride to only add one equivalent. Remember, lithium aluminum hydride, LiAlH4, with its 4 equivalents of hydride, will reduce the crap out of everything. They will reduce everything as far as it can get reduced, whether that be an alcohol or an alkane or something else along those lines. Lithium aluminum hydride will reduce everything. When we use lithium triterbutoxy aluminum hydride, you only get one equivalent of H. And that means that we can only add one H to our carbonyl. So the H will add as a nucleophile to the carbonyl. The electrons will go up onto the O. They will then come back down off of the oxygen, come off the chloride, and you end up with the aldehyde. No further reduction occurs when you use this reagent. Now, just as a note, you can convert an acid into an acid chloride using SOCl2, thionyl chloride, which is a reagent that we've seen before. It is useful in a lot of contexts, one of which is to convert a carboxylic acid into an acid chloride. We can then convert the acid chloride into a hydride using LiAlHOTBU3, this lithium triterbutoxy aluminum hydride. This ensures only one equivalent of H gets added. There is a carbon analog to this. Remember that not only lithium aluminum hydride would add multiple times to our special carbonyls, but Grignard's and lithium reagents added multiple times to our special carbonyls. If we only want one addition of a Grignard or lithium reagent to our special carbonyl, we use something called a lithium dialkyl cuprate. Sometimes people call these just cuprates. They're also called Gilman reagents sometimes. Notice that what you have is R2CuLi. There are 2 R groups on the copper, and that gives us a copper minus, and that is paired with a lithium plus. The cuprate reagent will add 1 R group to our carbonyl. The electrons will go up onto the O, come back down off the O again, kick off the chloride. That gets us to our ketone, but now we don't have any other R groups to add back into our ketone. Remember that a Grignard or lithium reagent would add back into the ketone again. If you only have the Gilman reagent, if you only have this cuprate, it'll only add once. So very useful because we are able to now add 2 equivalents or 1 equivalent, depending on whether we want to add 2 H's or 1 H, or 2 R groups or 1 R group. We can either use lithium aluminum hydride or lithium triterbutoxy aluminum hydride, or we can use a Grignard or lithium reagent or the lithium dialkyl cuprate Gilman reagent. While we're on the topic, let's talk a little bit about nucleophilic addition to the carbonyl. You probably remember this. We mentioned this when we looked at addition of Grignards to carbonyls, is that on the carbonyl, the highest energy bond is the C double bond O pi bond, which means that the LUMO, the lowest unoccupied molecular orbital on these functional groups, will be the C double bond O pi star antibonding orbital. That is the orbital into which the nucleophile adds. So, since that orbital is above and below the plane of the sigma bond, it's a pi orbital, so it's above and below the plane of the sigma bond, the nucleophile can add from the top face of the carbonyl or the bottom face of the carbonyl. That gives us an alkoxide because our leaving group is the pi electrons because we're adding into the pi star antibonding orbital. That gets us an alkoxide, which we could then protonate into an alcohol. That's our typical, say, Grignard addition to a carbonyl. Here we're using ethyl magnesium bromide again, adding an ethyl group to our acetone, our dimethyl ketone. That gets us our ethyl addition and the OMGX. After protonation, we get the butanol. If we use a hydride, for example, lithium luminohydride or sodium borohydride, it's the hydride that adds, not the ethyl group that adds, as in the case with the Grignard. So that gives us a reduction where we convert, say, the acetone, the ketone, down to the propanol, 1, 2, 3, a 3-carbon alcohol. Ketones and aldehydes are closely related to a type of functional group called a hydrate. A hydrate is essentially a geminal diol, that is to say, a carbon that contains 2 alcohols or 2 alcohols on the same carbon. They are related to the hydrate in the sense that there is a near 50-50 equilibrium with the hydrate and the ketone or carbonyl. So if we've got a ketone in the presence of acid and water, we can protonate the carbonyl using our acid, and then water will add to the carbonyl, displacing the electrons onto the oxygen to get us back to a neutral oxygen. That gives us our OH from our carbonyl and water on our carbonyl carbon. If we then remove one of those hydrogens from our water using a molecule of water, we regenerate our acid. So this is an acid catalyzed reaction. And now we have 2 OHs on our carbonyl carbon. That is a hydrate. And notice that every step along this pathway is equilibrium. This is a nearly 50-50 equilibrium, meaning that anytime you have acidified water in the presence of a ketone or aldehyde, a significant proportion of that ketone will exist as a hydrate. Also, that means that if you have a hydrate, it'll often convert back to the carbonyl. This can happen in acidic conditions, like I show here, or under basic conditions by simply addition of the hydroxide to our carbonyl, just delocalizing the electrons onto the O, and then reprotonating it from water. Now we have our 2 OHs. Where again, one of the O's was from our carbonyl, the other O came from the nucleophile, whether it was water under acidic conditions or hydroxide under basic conditions. In the next chapter, which is the alpha substitutions chapter, we're going to spend a lot of time looking at reactions that are related to this hydrate equilibrium. Just as a side note, there's also a useful functional group called a cyanohydrin, which is basically a carbon that contains an alcohol and a nitrile. That's called a cyanohydrin. You can make cyanohydrins by addition of a cyano group, a C triple bond N minus, a cyanide, to an aldehyde or a ketone, for example. Here, this is our nucleophile. Our C minus will add to our carbonyl, displace the electrons onto the O. We can reprotonate that O from some source of hydrogen, for example, HCN. If this is from NaCN dissolved in water, we would have water floating around. Protonation from some source to give the alcohol. This is cyanohydrin. We can also make another interesting functional group called imines. We can make an imine from a primary amine. This primary amine will act as a nucleophile. The N will add to the carbonyl carbon, displace the electrons onto the oxygen. That will eventually get protonated. We'll end up with an OH from our carbonyl and an NRH from our primary amine. That is also at equilibrium with the Schiff base. We lose water and we'll end up with the Schiff base. Here's the mechanism again. Protonate the O from our acid. The amine will add to our carbonyl. Electrons will go up onto the O. We'll end up with an OH and an R and H. We can lose a hydrogen, some proton transfers involved there, losing an H, gaining an H. Eventually we get to this intermediate called a carbonylamine. That will then undergo another reaction to get us to our imine, which is called the Schiff base. I'll move that up here. From our carbonylamine, if we protonate the O again, that will get us water. That water is a good leaving group because if it falls off, we end up with a resonance stabilized carbon. That C plus that it leaves behind is resonance stabilized by the nitrogen donating its lone pair in to make a pi bond. In fact, that's the major resonance contributor. The carbon here does not have an octet. In the major resonance contributor, our carbon does have an octet. Nitrogen has an octet under any case. So most of our molecule will spend most of its time looking like the major resonance contributor. If we can lose a hydrogen from that nitrogen, we end up with what's called an imine or a shift base, the C double bond N with an R group on it. Now, this reaction has what we call a large scope, meaning that the R group on the shift base, which here they're labeling Z, could be just about anything. And depending on what that Z group is, you get a whole slew of functional groups from that. If it's an H, so example, H2NH will get us that. Then our product is an imine. We'll have C double bond NH. If it's an R, so H2NR, a primary amine would be our nucleophile here, then our product will have the C double bond NR. That's also called an imine, but specifically when that's an R group, it's called a shift base. If we use an OH, meaning we're starting with something like hydroxylamine, H2NOH, then our product will be C double bond NOH, and we call that an oxime. If we use NH2 as our group, so if we have H2N and H2, that's hydrazine, then our product is called a hydrazone. Whatever, again, you can see the trend here, whatever Z group we have on our amine, that ends up on the C double bond N. So we can have a regular imine, we can have a shift base, can have an oxime or a hydrazone. If we use this NH phenyl group, this phenylhydrazine, our group is called a phenylhydrazone, NHPH. These are highly conjugated systems. If we use this NHC double bond NH, we end up with what's called a semicarbazide, and our product is a semicarbazone. So all these different functional groups can be achieved by using this type of a reaction as our general template. Now, we've seen reactions of ketones and aldehydes before, where we end up with what we call incompatible functional groups. Let's say, for example, we want to make this molecule. We want to make a target compound that has an aldehyde and an alcohol, and we envision that we can make that by starting with a carbonyl and a Grignard reagent that contains our aldehyde, and we can envision our Grignard attacking our carbonyl, getting our OMG Br that we then protonate to our alcohol, and there's our product. Basically, our aldehyde is such something that comes along for the ride with our Grignard reagent. The problem is that Grignard reagents themselves add to aldehydes, which means that in our mechanism, we have two targets for our Grignard. Our Grignard could add to an aldehyde, or a Grignard could add to the ketone. Well, the ketone is less reactive than the aldehyde because that aldehyde is more accessible. The aldehyde only has one R group and a hydrogen, whereas the ketone has two R groups. So by definition, these aldehydes will always be more reactive than the ketone. The point is that we've got incompatible functional groups. We've got functional groups together in the same reaction mixture that could react with each other, but we don't want them to in this context. So in that case, we can use something that's called a protecting group. Now, I want to mention that there are volumes and volumes and volumes and volumes of books that have been written and published on different types of protecting groups. Any imaginable conditions, there have been protecting groups that have been studied for those conditions. But for us, we're going to look at a very specific kind of canonical example of a protecting group. What we use is something called ethylene glycol. This is a 2-carbon vicinal diol. So 2 carbons, and each carbon has an OH group on it. And we need a little bit of acid. It's catalyzed by acid. Here's what we would want to do. We're going to use this ethylene glycol as a protecting group. When that ethylene glycol reacts with the aldehyde, notice that we haven't even made it into our Grignard yet. When this ethylene glycol reacts with our aldehyde, it turns it into this 5-membered ring, the CORRO 5-membered ring. That is a masked aldehyde. This is a group that is no longer susceptible to nucleophilic attack. It's no longer an aldehyde either. It's no longer susceptible to nucleophilic attack, but it can be reconverted back into the aldehyde in a later step. So our first step would be to protect our aldehyde using ethylene glycol. Then we can convert our bromine into a Grignard. Now we no longer have incompatible functional groups. So when we introduce our Grignard to our ketone, those are the only 2 viable reaction partners. And our Grignard will add exclusively to our ketone, get us our product or something that's close to our product. But then in the last step, what we can do is add acid. And that will do 2 things. Acidified water will, first of all, protonate our alkoxide into our alcohol, but it will simultaneously deprotect our aldehyde and get our aldehyde back. So we use the protecting group to hide the aldehyde from the nucleophile so that the nucleophile will go after a different target. Then after the nucleophile had been completely used, then we could reveal our aldehyde again. Aldehydes are more susceptible to protecting than ketones are, again, because aldehydes are generally speaking more reactive. If we have a molecule with ketone and aldehyde functional groups, and we only use one equivalent of ethylene glycol, that one equivalent of ethylene glycol will protect the aldehyde and not the ketone. That would then allow us, hypothetically, to reduce the ketone in the presence of the masked aldehyde, and then in a later step, reveal the aldehyde again. And notice that we have now specifically reduced our ketone to an alcohol without touching the aldehyde that was there originally. Here's the mechanism for protection. It's a pretty straightforward mechanism. It involves first protonation of the carbonyl, in this case a ketone. That gets us a resonance stabilized ion, which, by the way, is the reason that carbonyls are readily protonated. The reason that the oxygen on these carbonyls is readily protonated is because when it is protonated, you end up with a positive charge on the O that can be delocalized onto the C. So we get a resonance stabilized carbocation. Then our ethylene glycol will act as a nucleophile. It'll add into that carbocation. We then do a proton transfer where the alcohol will grab the extra H off of our ethylene glycol oxygen. That gets us water. Water can leave to get a resonance stabilized carbocation that is resonance stabilized by the carbonyl here. The other oxygen in our ethylene glycol can then add back into that carbonyl carbon that has positive character. That gets us our 5-membered ring. We have now closed the ring, and eventually by some later step, we can lose an H back to our solution. Remember here we had H plus floating around in solution, so we can regenerate that H plus by having our H plus fall off, and lo and behold, here's our protected carbonyl. The mechanism of deprotection is the same, except that it's in reverse. Follow this. If we start with our protecting group and we protonate it, we will end up here. That means that this group could release and we would have a resonance stabilized carbocation. Basically, we would have a leaving group now. We get a resonance stabilized carbocation. If water added into that carbocation there, we end up with this intermediate. We can then do a proton transfer from the water back onto our ethylene glycol group. That gets us this. Our ethylene glycol could then fall off as a leaving group. We would end up with a resonance stabilized carbocation, which from the carbonyl form we could lose our excess H plus and we'd be back to our carbonyl again. So practice writing out this mechanism in the forward direction and also try to write out the complete mechanism in the reverse direction, following the same procedure here, but showing the arrows going in the proper direction for deprotection as well as protection. One last important reaction from this chapter is called the Wittig reaction. It's spelled with a W, but it's a German word, so you pronounce it Wittig reaction. The Wittig reaction is very cool because you can take a ketone or aldehyde and introduce it to a new type of group that we're going to look at, which is called an ylide. In this specific context, we use phosphorus ylides in the Wittig reaction, but that allows us to take a ketone or aldehyde and create an alkene from it. Notice that we've got the two R groups, R prime in green from our ketone or aldehyde, and we've got an R and an H on our ylide here. Notice that this carbon in black with the R and the H is the carbon with the R and the H in black that ends up double bonded to our green carbon. It almost looks like the functional reverse of the oxidative cleavage by ozonolysis. In ozonolysis, we would start with an alkene and cleave that C double bond C to make the ketone or aldehyde. Here, we're starting with the ketone or aldehyde, reacting it with the phosphorus ylide, and reassembling that into an alkene. Think about phosphorus as being like nitrogen, but since nitrogen does not have access to d orbitals, but phosphorus does, phosphorus can make 5 bonds, whereas nitrogen cannot. But in all other contexts, phosphorus is like nitrogen. It likes to have 3 bonds with a lone pair. It's positive when it's got 4 bonds and no lone pairs, but it's also neutral when it's got 5 bonds because it has d orbitals that it can access. So we can make a phosphorus ylide by starting with triphenylphosphine, PH3P, and adding an alkyl halide to it. So our phosphorus will attack our carbon, displace our X. Now, notice that we have added a carbon and any other R group to it. We can then introduce a strong base, like again, N-butyllithium, and that strong base will remove one of our hydrogens from that carbon. That gets us this P plus, C minus. Again, normally these H's on carbon are not acidic, but because they are adjacent to a phosphorus, they can be removed so that you end up with a C minus that is stabilized by the adjacent phosphorus. The electrons from the carbon could be donated to the phosphorus as a pi bond. That would give phosphorus 5 bonds and be neutral, carbon 4 bonds and be neutral. That's the ylide. What we're looking at here is the ionic form, the ionic resonance structure of the ylide. So that's how we can make the ylide. We can then use the ylide to attack the ketone or aldehyde. That C minus, carbon with negative character, will add to the carbonyl, displace the electrons onto the oxygen. We get this intermediate called a betaine. That's not a particularly important intermediate, except that it does put the O minus and the P plus in relatively close proximity to one another. And oxygen and phosphorus make really strong bonds with each other. They love to bond with each other. So what will happen is from that betaine, the O minus will add to the P plus, get us back to our neutral state, O with 2 bonds, phosphorus with 5 bonds. That's called an oxaphosphatane. Notice it's a 4-membered ring. That's not particularly stable. So what will happen is it will collapse. We'll take the electrons from the CO bond, move them to make a double bond between the P and the O. Again, phosphorus loves oxygen bonds. So we'll take those electrons and move them to the PO location, give us a PO double bond. Then that forces the phosphorus to release its carbon. Those electrons can fall back down to make the C double bond C. So that's where we get our carbon-carbon double bond, and we lose this triphenylphosphine oxide. One thing also I forgot to mention, another reason why this P plus is so stable, not only is it next to a C minus, but it's also got three phenyl groups on it, which makes this phosphorus essentially the benzylic position. It's that P plus is adjacent to three aromatic rings. So very highly stabilized positive charge also gives us a very stable negative charge next to it. The fact that that phosphorus P plus is triply benzylic means that it spends a lot of time in this resonance contributor form and not necessarily so much time in this resonance contributor form, even though this is the neutral form. This ionic form is really stable, more stable than you might think. So that's the Wittig reaction, and we can use it to make all kinds of alkenes. Notice that whatever groups are on our carbonyl and whatever groups are on our ylide end up being the groups that are on our double bond. So think about this. If we want to make this double bond, we've got a carbon with two methyl groups and a carbon with an ethyl and a hydrogen. We could imagine, again, retrosynthetically, imagine disconnecting that double bond. Say, how could we make this double bond using the ylide? If we disconnected it this way, such that we would have a dimethyl carbonyl, so the two methyls would come from the carbonyl side, and then the ethyl and the hydrogen would come from the ylide side, or we could disconnect it so that the ethyl and the hydrogen would come from the carbonyl side, and the dimethyls would come from the ylide side. Now, the book tells us that this is preferred. The method that puts the two methyls on the ketone and the ethyl and the hydrogen on the ylide is preferred over the one that puts the two methyls on the ylide and the ethyl and the hydrogen on the ketone. Why would that be? Well, remember that C minuses are unstable, generally speaking, and the more substituted the anion, the less stable it is. That's the opposite from the cation. So more R groups on a C minus is bad. So if our choice is to start with a dimethyl ketone and then a ylide with only one R group on it, or start with a ethyl aldehyde and then start with an ylide with two R groups on it, we might as well choose the pathway that lets us use a more stable ylide, a better ylide. On paper, you could use either one, but if you had the choice, and you always will have the choice, when you're making a double bond, you'll have the choice to make it from a Wittig reaction, and then you can choose which side, which part of the double bond comes from. You want to choose the side that lets the ylide have the less substituted side. So our carbon with the hydrogen would be the ylide side, and the carbon with the R groups would come from the ketone side. Some other reactions, some of these are review, some of them are new. We looked at oxidations and reductions. So go back to our alcohols lectures where we looked at all the oxidations and reductions in our oxidation reduction map that involved interconversion between ketones and aldehydes. We looked at the Clemmensen reduction from our EAS lecture. There's another reaction that is analogous to the Clemmensen reduction that's called the Wolff-Kishner reduction. And that is like the Clemmensen reduction in that you can convert a carbonyl into an alkane, simply reducing that oxygen, that C double bond O, to two H's. The Clemmensen reduction does it when the carbonyl is attached to the aromatic ring. It also uses acidic conditions. The Wolff-Kishner reduction does not require the carbonyl to be attached to an aromatic ring. It can be aliphatic. These can just be regular R groups. Also notice that this uses basic conditions. First, what we can do in the Wolff-Kishner is convert the carbonyl into a hydrazone using hydrazine, NH2NH2. Then, under basic conditions, react the hydrazone with KOH, and that will displace the N bond as a N triple bond. We'll lose water from our water and our two hydrogens. We'll lose our two N's as N triple bond N, and we just end up with a normal carbon with two hydrogens on it. If you want to try to figure out the conversion of the hydrazone into the alkane here using H2O and KOH, go for it. The leaving groups are going to be water and N triple bond N. Lastly, I want to tell you about a non-spectroscopic method of detection of aldehydes. Remember, we looked at lots of ways using spectroscopy to detect aldehydes. For example, NMR, we can detect aldehydes by looking around 9 to 10 ppm for aldehyde hydrogen. In IR, we can see the aldehyde carbonyl at 1725 and the aldehyde CH bond at 2700 and 2800. There's all kinds of great ways using spectroscopic methods to determine whether aldehydes are present. One of those chemical methods for detecting aldehydes is called the Tollens test. It uses something called a Tollens reagent, which is a silver ion that is complexed with two ammonia molecules, so Ag plus NH3 and hydroxide. And when we react an aldehyde with the Tollens reagent, the silver gets reduced from silver plus to silver metal, Ag0. And the aldehyde gets oxidized from the aldehyde to a carboxylate. We end up also making ammonia and water along with that. But this is a useful reaction for detection of aldehydes because the product is silver. In the presence of the aldehyde, you end up with metallic silver that will cling to the bottom of your reaction vessel and make a mirror-like coating inside the reaction vessel. Now, this is a destructive method. Remember, I talked about how many of these chemical methods for detection of functional groups are destructive. They convert the functional group into something else, and it's the product that indicates that the functional group was there in the first place. So if your aldehyde is valuable to you, or if it's expensive, or if it is difficult to make, or something like that, if it's harvested in low yields from nature, you don't want to use a Tollens test in order to figure out if you have it there, because you will destroy your aldehyde by converting into a carboxylic acid. Also, notice that a product of the Tollens reagent is silver metal. If you get a hold of a bottle of the Tollens reagent and you can get your hands on some cheap formaldehyde, all you have to do is react the two. The Tollens reagent will oxidize the formaldehyde to formic acid, and you'll get a bunch of silver at the bottom of your reaction flask. And silver is really expensive. The Tollens reagent is an expensive reagent because it contains silver. So this is an expensive method for detecting aldehydes. But I can almost guarantee you that the ACS exam will have some question involving the Tollens test. They love to ask about this. They love to either ask about what the product will be if you react a Tollens reagent with an aldehyde, or it'll say what reagent or what reactant will be detected if you use this Tollens reagent. They use it all the time on the exam. So just be aware of the Tollens test for converting aldehydes into carboxylic acids. Okay, that's the end of lecture 9, our ketones and aldehydes chapter. There was some new material here. For example, the lithium tri-tert-butoxy aluminum hydride and the Gilman reagent and the Wittig reagent. Those are all new reactions, so don't forget to add them to your reaction maps. If you're making reaction maps, don't forget to make flashcards out of them. If you do have reaction maps, make sure you make all of these connections with our older reactions. Make sure that if you have other reactions involving ketones and aldehydes, that you connect those ketones and aldehydes to our alkenes and our alkynes from our older chapters.